The last episode built the dual space. Next question. Given a subset, which functionals in the dual vanish on all of it? The book calls that set the annihilator of the subset. Orthogonality first appears in this dual setting, but the word waits for Chapter 5. The definition runs the other way too. The vectors that every functional in a subset of the dual sends to 0 also form an annihilator. 2 of the 5 exercises matter here. The span changes nothing, and every set sits inside its double annihilator. Then a dimension identity. If W is a subspace of V, the dimension of V is that of W plus that of its annihilator. The proof extends a basis for W to a basis for V and looks at the dual basis. The functionals matching the added vectors span the annihilator. A corollary follows at once. The double annihilator of any subset is its linear span. Apply the identity twice, and the two have the same dimension. The span already sits inside the double annihilator, and with equal dimensions they must coincide. Now the adjoint. Take a linear map from V to W and a functional on W. Compose them, and you have a functional on V. The correspondence this defines is a linear map from the dual of W to the dual of V, and it is called the adjoint. Notice the arrow has reversed. The first theorem, sending a map to its adjoint, is itself an isomorphism. Linearity comes from composition being bilinear. If the map is not 0, find a vector it does not kill and a functional non-zero on the image. That gives injectivity, and the dimensions match. The same theorem has a second half. For 2 maps composed in turn, taking adjoints reverses the order. That is no accident. The adjoint pulls functionals backwards along the map, and going backwards, the step applied last is the one met first. The second theorem trades null spaces for ranges. The null space of the adjoint is exactly the annihilator of the range of the original map, and the annihilator of the range of the adjoint is exactly its null space. The proof only unwinds the definitions. The dimension of the range of a linear transformation is its rank. Putting the last 2 theorems together, the adjoint has the same rank as the map it came from. Later this becomes a known fact about matrices. Rows and columns span spaces of the same dimension. A special case, a map with a one-dimensional range. Pick a non-zero vector in it. The map sends each input to a coefficient times that vector, and the coefficient is linear in the input, so it is a functional. The book calls this a dyad, and its adjoint is 1, 2. Finally, what natural means. Every space has its own isomorphism onto its second conjugate. Take any map from V to W and draw a square. The map along the top, the adjoint of its adjoint along the bottom, the isomorphisms down the sides. It always commutes.